everyone. Welcome to Bilecik Algebra Number Theory Seminar. And with my pleasure, next speaker is Professor Mike Bennett from University of British Columbia, and he will speak about arithmetic progressions in some sets of geometric progressions. Thank you.
Oh, well, thanks very much, Ilker. It's a great pleasure to be invited. A couple of words. There's some very nice words in the title. There's been some very interesting work done in the last few years on questions about arithmetic progressions. There's been some very interesting work done on questions about sumsets. Let me just mention some of these things, and then I'll give the disclaimer that what I'm going to talk about is nothing to do with the interesting stuff. But nonetheless, it's related in a little way to both of these. So just to remind you, we have these sort of sum product formula. You take a couple of sets, you look at the set of all things you get by doing pairwise sums or products, and there's a conjecture that these sets, in some sense, let's think of these as maybe being finite sets, so maybe just counting sets up to some level of some collection of integers, that basically the idea is that one or both of these should be large, that it's not possible to have both of them simultaneously, in some sense, unexpectedly small. And so this is a sort of conjecture of Erdős and Szemerédi, dating back a long time. And there's been some really beautiful work on this, where we've had a lot of really recent work sort of sharpening this or generalizing it, going in various different directions, going back to, we actually have a theorem rather than a conjecture where the lower bound you can replace the exponent 2, which would be best possible, by 4/3, and this has been improved and taken in many different directions. So it's beautiful work done in the past few years on this. But that's not what I'm going to talk about. So unfortunately, people who tune in for that, this is a disclaimer that that's not where we're going here. In another direction, if we don't want to talk about sumsets, we can basically ask the question, if we take a set of integers, how basically deep must this set be to contain, say, three-term arithmetic progressions? We could ask this for higher, for 4 terms or 5 terms, etc. And of course, we have beautiful work of Green and Tao answering this question, where you have the sets of primes and you have arbitrarily long arithmetic progressions. So this is a question where, again, there's been really beautiful recent work of Kelly and Mika, which basically gives us a bound that's almost the right order of magnitude for how big a set must be to guarantee. So just on density argument, so nothing to do with the structure of the set, to guarantee that there's three-term arithmetic progressions, or you can twiddle this to like infinitely many three-term arithmetic progressions. So this is a really beautiful result. And just to mention that these are by two, I believe, computer scientists and sort of people who had worked very hard on this, turn around and analyze their argument, were able to improve the 1 over 12 to roughly 1 over 8. But really a beautiful result. And the thing that makes this most striking is A, that it's sort of orders of magnitude better than the previous bounds. This, again, previous bounds guaranteeing that if you're a set beyond a certain size, you're guaranteed to have three-term progressions. This is something that's sort of quantitatively much stronger. And it's almost getting to the point where it's the other direction, where there's a construction that goes back a long way to Behrend to construct sets that are devoid of three-term progressions, and it's almost the same size. So it's almost right at that boundary. So it really comes down to understanding that exponent. So right now, it's truly a breakthrough result. So that's really striking stuff from the past few years. I'm not sure this has even been published quite yet. But sadly, for people tuning in, the talk isn't about that either. So it's just lots of words are the same, but what I'm really going to talk about is a different question entirely. So I'm going to look at sort of starting point might be a couple of sets of geometric progressions. I'll take A to be the set of non-negative exponent powers of 2, and B to be the geometric progression you get by looking at powers of 3. And you look at the sum set of this. So you're looking at the set of integers of the form 2 to the A plus 3 to the B. Maybe I shouldn't use A and B for that, say alpha and beta. And there's a paper appeared in the archive a couple of years ago by Chen, Huang, and Shang, proving that this sum set contains no 7-term arithmetic progression. So it's not making a statement about other things, but it's interestingly enough, it's sort of sharp. So if you like, it's saying, okay, if you take a look at this set, then the longest arithmetic progression has length less than or equal to 6. And in fact, there are two arithmetic progressions in this set that have length exactly 6. So this is sharp. And what's interesting about this, it's the sort of thing, if you look at the argument, you'll see pretty quickly kind of how it'll work. That basically you take a bunch of terms in progression and you notice that, for instance, if you call those so n plus d, n plus 2d, etc., you notice, for example, that n plus twice d, let's suppose everything is positive, is bigger than 1/2 of n plus 4 times d because twice n plus 2d is 2n plus 4d, so it's bigger than n plus 4d. And so if you have enough progressions, that they're in some sense quite close together in size. Now, if they're built up by summing powers of 2 and 3, that tells you that the exponents have to match up, right? If you have the biggest exponent on 2 is, say, kappa, the biggest exponent on 3 is, say, gamma, then you have another term which has also an exponent equal to kappa or equal to gamma. And then you can play around with this. If you have enough of these sort of coincidences where the things actually have similar exponents, then that would actually give you, through a little bit of cancellation, a very elementary combinatorial argument, that would give you a three-term arithmetic progression actually in a geometric progression. And that you can prove very easily doesn't happen. So it's a very elementary argument, but it turns out in this case to be kind of sharp. So was sort of the starting point for me, was to look at this and to try to understand this on different levels. So the first comment to make is that this argument doesn't actually tell you anything about six-term progressions. So it doesn't tell you, for instance, there's finitely many in the set, or anything at all about three-term, four-term, five-term. So it's an elementary argument that really does assume, to start with, that you have seven terms in arithmetic progression in the set, and then uses that to derive a contradiction. So and if you do a little computation, it's very easy to compute here because these sets grow so quickly. If I want to say I'll find all of the three-term progressions low down, say bounded by 10 to the 20, this is a very short computation. You could do this with any computer algebra package. And if we look at this set, A plus B here, you find the two six-term ones I described. You find 6 five-term, 25 four-term, and 373 three-term. And more generally, if we look at this, we can look at the sum set of powers of A and powers of B, where let's suppose that A is at least 2 and B is bigger than A. Here, for the purposes of this, I've assumed that they're relatively prime, but you don't have to. So our main theorem won't make that assumption. And we just go and look at this, look at the three-term progressions. And again, this is a short computation. It's just to sort of suggest what might be going on. And so here I'm just tabulating the numbers of these we run into. So, and this is, for certain choices. I made certain choices to what to go on. So for instance, if A is 7 and B is 9, I don't find any. But again, we have 373 for 2 and 3. We have 148 for 2 and 17. And we'd like to have an idea of what's going on. So if you settle down to prove this, I should point out before we go on that there's structure going on here, of course. These are very structured sets. Just based upon, if we look at this sum set A plus B, just based upon how they grow, well, if you count the number of things that are a number of elements in A plus B up to X, it's going to be asymptotic to a constant times the log squared of X. So this is in some sense a very thin set, much, much thinner than the primes or the squares or anything like that. So it's a terribly thin set. And so no general result is going to tell you anything about three-term arithmetic progressions. In fact, probabilistic arguments say if you take a random set that's this thin, there shouldn't be any three-term arithmetic progressions. Okay? So it's sort of unusual that there are arithmetic progressions at all, but again, it's a very structured set. So here is quote unquote the truth. So I'll define S of A comma B. This will just be my sum set. I had this A plus B before, big A plus big B. So it's a set of these things. And a conjecture one would make, and it's a conjecture that I can't quite prove, sadly, but one should be able to, perhaps, is that, in fact, you get three-term arithmetic progressions, sometimes infinitely many of them, and sometimes you don't. And in fact, you should have infinitely many exactly in two situations. Either A, if they're relatively prime A and B, then A should be 2 and B should be a power of 2 plus 1. So if we go back to this, pardon me, I'll go back 1, then this is the case here. This is the only case I'm looking at. It's a relatively prime case. When B is 3 or 5 or 17, there should be infinitely many. And there should be finitely many otherwise. Okay? And the other possibility is if A and B are multiplicatively dependent. So, for example, if A is 4 and B is 8, multiplicatively dependent means some non-zero power of A is equal to some non-zero power of B. So 3 and 9, 4 and 32, things like that. So in those cases, so in these cases we've listed here, these particular sort of special cases, you can prove there's infinitely many three-term arithmetic progressions. Just a construction, you can write them down. So the question is the other direction, sort of eliminating that possibility. And it does seem that even with pretty heavy machinery, we can't quite prove this, though it's true under most conjectures one might reasonably believe. So what's interesting here, the structure changes quite a bit. So if you look at this set, this is the sum sets of powers of 2 and powers of 7, you can prove that there's exactly 22 three-term progressions. If you look at powers of 2 and powers of 9, there's infinitely many. And powers of 2 and powers of 8, you can even prove there's infinitely many, not just three-term, but there's infinitely many four-term. So again, none of these things would be predicted by just probabilistic arguments based upon how dense these sets are. These sets are very thin. You don't expect three-term progressions. But it's interesting here that, for me at least, that the structure is something you can actually describe so neatly. And moreover, that the proof, well, the almost proof of this is actually quite hard. So what can I actually prove? Well, I'm not going to prove this something related to this conjecture. I'm going to focus on the other direction. So instead of analyzing when you have infinitely many three-term progressions, which again we can just about prove, but not quite, what the situation is, instead I'd like to look at it and say, okay, well, when do we have longer progressions? So here, what do I mean by longer? I'm looking at five-term progressions, 5 or higher. So this theorem here completely characterizes every situation where for any A and B, there's a five-term progression or longer. So we saw in the case where A equals 2 and B equals 3, there were two six-term progressions. So here it says, okay, there's actually these infinite families where there are five-term progressions. There are infinite families of pairs AB, which we have these parameterized five-term progressions. So we have a five-term progression, for instance, with A equals 3 and B equals 108. Then we have these, I guess it's 9 special cases, and that's it. So the theorem, we can sort of explicitly characterize all the five-term progressions or longer, and we don't say anything about 3 and 4 term, which is a bit unfortunate. But there's technical reasons for this that I just can't prove the results, so sadly. So a corollary of this, if you go back to this, we can look at these things. These are all the five-term progressions, and we can look at this and find that, in fact, the six-term progressions, there's only the two that really come from A equals 2 and B equals 3. You can actually do the second ones, A equals 2 and B equals 9 as well. Okay. So there's only these two. So that says again for any other choices of A and B, there's never more than a five-term progression, and you can actually see for outside of these families. So for instance, if A is bigger than 3, there's never even a five-term progression. So we top out with four-term progressions, and in fact, we can find infinitely many pairs AB with A arbitrarily large that have four-term progressions. So in some sense, it's getting close to being sharp, but again, there's frustrating reasons it doesn't quite work. So let me tell you kind of how one goes about proving these things. And again, the thing to emphasize is that there's quite a lot of machinery goes into this proof, whereas the motivating paper is really purely elementary. It's kind of just a counting argument. It's really using the pigeonhole principle a bunch of times. So our approach then, if you look at this, if we had even one three-term arithmetic progression, then again, you have a three-term arithmetic progression. That means you've got a solution in the set to x plus y equals 2z. And that, in our case here, corresponds to this equation with 6 terms in it, a to the x0 plus b to the y0, etc. So this if we actually, so here A and B are fixed, so in particular their prime divisors are fixed, this is an example of what's known as an S-unit equation. So it's an equation where we sum up a bunch of, let's just say, good old rational integers. I mean, we can do the same kind of thing over number fields if we like, but we sum up a fixed number of terms where we are controlling the prime divisors. So this is something that, well, it's understood on some level, but it's understood only through pretty heavy machinery. So it goes back to results of Wolfgang Schmidt. It's really the subspace theorem that allows us to prove that such an equation has finitely many solutions. Well, we have to be careful there because we know each arithmetic progression gives us a solution. I've already told you that there's examples of A and B where there's infinitely many three-term arithmetic progressions. So in other words, there's infinitely many A and B for which this equation has solutions. Uh, there's infinitely many for a fixed A and B. There's infinitely many solutions to this equation, potentially. So I should tell you exactly how that works. So the starting point here, if we look at when a solve, so we want to solve unit equations. Here, the takeaway we're going to get is that we can't really solve this, but we can almost solve it, and we get some at least qualitative results about it. So the starting point here is what looks like you when you put this up in a talk, anybody will look at it, a non-mathematician will say, well, I can solve that. If x plus y equals 1, well, y is 1 minus x, we're done. But the idea here is that we might, this is sort of a classical way of looking at it. We could do this over number fields as well if you like. But in general, we take the x and y to live in some sort of finitely generated multiplicative group inside the non-zero complex numbers. So for example, if we actually look at all the rational numbers whose denominators and numerators are comprised out of powers of 2 and 2, 3, 5, 7, 11, or 13 up to sign, then we can actually show that this equation has exactly 545 solutions. So for instance, a half plus a half equals 1, etc. So these are all the solutions, and you can actually do this completely effectively. To solve this, you have to use bounds for linear forms in complex and p-adic logarithms. So this is a result that goes back to Benny de Wever in the 1980s. And these unit equations, they're interesting things. They pop up all over the place. So they pop up sort of, they arise very naturally in the case of, say, solving 2A or related equations. You use them to answer questions about integer points or S integer points on different curves of potentially higher genus. They show up in questions about recurrence sequences, about monogenic fields, irreducibility polynomials, that kind of stuff, producing all the given equivalence classes of forms, binary forms, say, of given discriminant. They show up in various different sort of transcendence criteria. They show up in funny places. There's been surveys about their applications going back to the 1980s, Cal Manjuri and his co-workers. So this is again, we're going to go back and forth between, if you like, homogeneous and inhomogeneous. So the homogeneous and inhomogeneous cases basically depend on whether you've got to have a 0 or a 1. If you say, well, this one doesn't have a 1, you could just divide through by a non-zero thing to get yourself, divide through by a n x to the x sub n if that's non-zero, and then you pick up a 1 and you move it around. So you can go back and forth between these two, and it just makes a difference in that it differs upon how many terms you have. You count. The count's different by 1 depending on where you start counting. So the idea here again is that you suppose you have some S units. So S will be some finite set of places over some number field K and containing the infinite places. And we'll look at this kind of equation. And we have to suppose further there's no vanishing subsums. I'll say what that means in a second. That means that we're not going to, so we've got a sum here, I'll get n plus 1 terms that sum to 0. I'll claim that we don't have any sum with fewer than n plus 1 terms that sums to 0. So in particular, these things are all going to be non-zero, and we don't have, say, 2 or 3 of them add up to 0. Okay? And we'll see, I'll show you why in a second that actually matters. So we'll call these, so assume we have those kind of conditions, then there's result culmination of lots of work, again, going back to Schmidt, done really initially for this kind of problem by Evertse, beautiful result that just counts the number of solutions. So it says the number of solutions, if you have so your subgroup of rank R, so if you like, you're counting the number of elements in S, you fix that, call that R. You've got a sum with, this is the term of the one now, with n of them, then you get this bound on the number of solutions. And this again follows from the sort of Archimedean and non-Archimedean versions of the subspace theorem. The subspace theorem is a beautiful generalization of Roth's theorem on Diophantine approximation, going back to Wolfgang Schmidt. So this is a beautiful result, and it's quantitative in the sense that it tells you how many there are, but it's unfortunately not effective for large n, larger than two. It's not actually effective in that it tells you how many solutions you have, but it doesn't tell you how to find them. It doesn't give you any bounds on their height. If you could bound their height, then at least theoretically you could search and find them. But here it doesn't give you anything like that. So this is very similar to Roth's theorem, where it tells you that some approximation holds for some algebraic number, but it doesn't tell you what the constants are. So the same thing here. So the problem for us is that to handle this kind of problem we started with, where we actually had, in this case, we'd have little n equals 5, we like to solve these equations effectively. We'd like to find bounds upon possible solutions so then we could search. And the problem is that a priori, in complete generality, we can only do this, again, I have to count this right, we can only do this in the case here where n equals 2. In other words, we're summing up three terms. That's the x plus y equals 1. And there we can do this effectively. So let me just show you how that works. So the thing to think about is, forget about even things being algebraic or not. Pretend you had three complex numbers added up to 0. Then what we could say, at least in sort of Archimedean absolute value, is that, well, at least two of them are kind of the same size. Right? You couldn't have one gigantic and the other small, because then by the triangle inequality, you couldn't have them adding to 0. So for general complex number off the shelf, two of them out of three have to be the same size. And the magic of linear forms and logs is that it basically says, no, no, no. If a bunch of things add up to 0, if they're algebraic, so put ourselves in our setting we had here, where these things are, say, living in some number field. So these things are nice and algebraic. The coefficients are nice and algebraic. Then what linear forms and logs allows you to say is that if a bunch of them add up to 0, then in fact the third one has to be kind of the same size. And it lets you do this, linear forms and different types of logarithms, kind of for whatever notion of size you want to use. So you fix a place. It might be, two-adic. It might be just the complex absolute value. And it says, hey, the third term has to be pretty big too. Okay? And so that's what I'm saying here. If you ignore this, it basically says that if you order them in size, then the x sub 2 must be pretty close to the same size as the biggest one. So you have three that are kind of the same size. Okay? And so that's the sort of rough thing. And this is where, if we just take a little deep breath and step back, this is where you need to actually assume this case we don't have vanishing subsums. So here's an example where we just take our things to be, say, powers of 2, and we add them up. Well, here are 4 powers of 2 with plus or minuses that add up to 0, where you notice that in Archimedean absolute value, the third one is not the same size as the first two. They're arbitrarily big. But this is a case of what's called vanishing subsums, that the 2 to the n and the minus 2 to the n add to 0. So we actually have 2 vanishing subsums here. So this is the case we're not just avoiding because we can't prove anything, we're avoiding it because none of the things we're going to claim are actually true in this case. So that's the setup here. So the idea for an S-unit equation in general is that the 3 largest terms are roughly the same size. And that's how you actually solve the 3-term S-unit equation. We actually have, for each place, the 3 terms are all kind of large. But the product formula says if you multiply together each of the places, you get 1. And so they can't all be big because the product can't then be 1. So that's effectively how linear forms and logs allows you to solve 3-term S-unit equations. And you can already see the problem for 4-term, that this argument doesn't really work. Okay. So the first person to actually take a look at this kind of problem, the problem of trying to do effective S-unit equations for a little bit more, just a tiny bit more than 3 terms. So was Paul Wojta, actually in his thesis, which is now more than 40 years ago. So in Voida's case, he looks at a four-term equation, so it's very special, and he puts very strong restrictions upon it. So he says, okay, well, we're going to have to actually restrict the number of primes. So in the classical case, if we're looking at going over the integers, an example where this would work would be to take the set S. It'll take the prime at infinity, but also say the primes 2 and 3. So we could take an equation where we add up four things where their only prime divisors are 2s and 3s, and if that adds to 0, then Voida's argument allows you to solve this effectively. So this is the first case where we go sort of beyond three terms. And the idea behind the proof is it's just a pigeonhole principle. So if then again, linear forms of logs tells you pick a place, then three of these four terms are big. And so the total number of pairs, if you look at the places here, is the number of elements of our set S, or that's our set of places. And then we've got four terms. So it's 4 times S. Then the argument before said, well, the number of big terms, if you add that up, is at least 3 times S. And so you subtract that and you get that the number of terms where you're small at a place is at most S. And so if S is strictly less than 4, you end up finding a term, one of the four terms are adding up, which turns out to be, by the pigeonhole principle, large at every place. And that contradicts the product formula. So that's Voida's argument, and that allows us to go in this very, very special case, because the problem is, if you say, try to add up four terms where you allow them to contain the primes 2, 3, and 5, this argument doesn't work. And that is something that's beyond effective technology, even currently. So I relatively recently, did something with a student, Prajit Bajpai, where we try to sharpen this result. And this is a very a little more complicated looking thing. It's basically, again, a pigeonhole principle kind of argument, but it basically says, well, we can solve systems of these S-unit equations if we have these very strong restrictions, again, comparing the number of equations to the number of elements in the set S. And you don't really need to read through this. It's set up this way because I wanted to apply it to solving what are called norm form equations, where you get these systems of equations that are just a single one. But if we restrict our attention to a single equation, then what this allows us to do is do exactly what Voida did with the same restriction, that the set S has to contain at most 3 elements. But instead of adding up 4 terms, to get 0, we're going to add up 5. So it generalizes Voida, lets us handle a 5th term. And the arguments, obviously, Voida's argument doesn't quite give us this, but the argument is a little bit different. So the idea is not that we can show that a given term is large everywhere. That would be a contradiction right away. But we could show that 2 of the 5 terms have to be large at the same places and otherwise small. So they're large at the same place and otherwise small. And if this is true, we can just take those 2 terms that sort of match up, if you like, at each place and add them together and rewrite that as something relatively innocuous, relatively small. So here, whenever I write these things, the a sub i's and a sub j's, they're just kind of small. They might be of logarithmic height compared to the x sub i's and x sub j's. So the idea is you can just sort of what we call matching. You can just take 2 of them, add them together, and get something relatively small times another S unit. And so if we can do that, then our sum of 5 terms reduces to 4 terms, and then we can employ Voida. And so that's the idea behind this argument. But I'll go back to where we're led. If we're looking at this sumset of the powers of A and the powers of B, then a single 3-term progression corresponds to an equation like this. And this, sadly, I've said, well, okay, if we control the primes dividing A and B and make they're few enough, then we can solve. So, for instance, if we make A is 2 and B is 3, that's only 2 primes. Add the prime infinity, that gives us the cardinality S is equal to 3. Then, if magically we had only 5 terms, we could solve that. But unfortunately, we have 6. And so, what we have to do, this, according to the theorem of Everett, this was a finite problem for fixed A, B, if there are no vanishing subsums. But unfortunately, the vanishing subsums can be quite complicated. So if I just restrict to the case where A and B are relatively prime, you can show quite easily, very elementary argument, the vanishing subsums always correspond to A equals 2. And if you go through, you can handle all these vanishing subsums and take care of them with one exception, very frustratingly. And the exception is a very particular case where this equation is a vanishing subsum. I can't remember quite which it is. It might be when a to the x0 is equal to twice a to the x1. So if you have that, no, it isn't that one. It's maybe it's a to the x2 equals twice a to the x1. If you have that one, that thing disappears, and you end up getting the equation I list here. This is 1 plus a power of b plus a power of 2 is equal to twice a power of b. And you might look at this and think it's a fairly innocuous looking equation. But remember, we want to solve this. It's a polynomial exponential equation. We'd like to solve this sort of simultaneously for all exponents and for all b. So this is a case where things can get very tricky. With polynomial exponential equations, a really famous one was the equation of Catalan that was taken care of by Mihalescu. And in Catalan's equation, there you've got, if you like, x to the p minus y to the q equals 1, where everything's a variable. So that's a polynomial exponential equation. And that was like remarkably tricky to solve and a beautiful result of Mihalescu. If you replace the 1 on the right-hand side by a 2, it doesn't look much different, but that's suddenly beyond current technology. So it's a frustrating situation that it reduces this equation. And as far as I don't know how to solve this equation. But I'll point out that if you have nothing to do with finiteness, so for a fixed b, it's fairly easy to show this is a finite situation. But if you have a fixed b, if there's even a single solution, then the set S sub 2 comma b has infinitely many three-term arithmetic progressions. So you can just write them down. So it's a frustrating situation that if there's even a single solution, my classification that's not one I expect. My classification of pairs AB with three-term arithmetic progressions, infinitely many, suddenly fails. And I'll point out for this equation, here's the equation up in the title again, that if you actually have b is a power of 2 plus 1, then you always get a solution to this. So this is what gives you three-term arithmetic progressions in these particular sets, like a equals 2 and b equals 9, or a equals 2 and b equals 3. And the problem is I can't rule out the possibility that there's other solutions. So it's a very frustrating thing. It looks like it should be easily approachable by a something, but I don't know how to do it. It doesn't seem that there's local obstructions. I'm not sure how to approach it. So again, if we assume, I think, plausible conjectures like the ABC conjecture, you can show that this thing should have finitely many solutions and none beyond a certain point. But it doesn't seem to be a consequence of linear forms and logs. So p-adic or complex. I wasn't able to make it work, at least. Maybe one can, in which case one could have a nice classification. Okay. So if we don't have a vanishing subsum, then in fact we can use the kind of arguments I use in the paper with Baj-Pai to solve these things effectively. So in these cases, we can do things. So in particular, for any a that's bigger than 2, at least if a and b are relatively prime, there's never vanishing subsums. And so we really can solve this problem of having three-term arithmetic progressions. We can really classify them. So by way of example, we can show that it's just a randomly chosen example that if a is 7 and b is 8, then there's exactly two three-term arithmetic progressions, and here they are. So I just want to mention the machinery we use. So this is a sort of a special case of the results I have with Prajit Baj-Pai, that this is the case, again, I said we could handle 5 terms where the S had cardinality 3. In this case, this is an S with cardinality 3. It's the primes 2, 3, and infinity. And here's the 5-term thing. And we can explicitly solve this. If you count them in a certain way, the solutions, you can show there's exactly 1,431 solutions to this. Counted correctly, I guess, maybe ordering the solutions in a certain way with no vanishing subsums. Of course, with vanishing subsums, things go wrong. And you can write them down. It's a little bit shorter to write than the way I've written here by just saying, hey, the biggest term that ever shows up is 3 to the power 12, and all the exponents of the 2's are bounded by 19 and the 3's are bounded by 12. So this allows you to actually use, so we need this. So this is a piece of machinery. This uses a lot of linear forms and logs, and this we need to prove the result we're talking about. Then that's five-term S-unit equations. For smaller ones, so three-term, this goes back to De Vegher. I said there's 545, and this is a statement of it. This is with this is we need to be able to handle more than just two and three here. We need to be able to handle things divisible by primes up to 13. So De Vegher gives us that, and explicit way to find them. Again, he tabulates them in his thesis. And then the sort of more explicit version of what Voida had done was worked out later on. Actually, I think in the first paper that Chris Skinner ever wrote, which I think he was 14, and it was in Journal of Number Theory. He wrote a paper where he sort of independently discovered what Voida had done, also in the 1980s. Uh, and then Rob Tiedemann and a couple of his students, Wang and later Deze, actually worked out some of these explicitly. So these are explicit four-term equations and valid for all primes up to 200. For our purposes, we just, I think, need it up to about something like 11. Um, so uh, these are some of the ingredients that come in. All of these ingredients we need. So if we step back and think about trying to do the same kind of argument that those three Chinese authors did in the archive paper, where they use an elementary argument to handle the case with a equals 2, b equals 3. When a and b are much larger, the elementary argument actually becomes simpler. So because again, if I have, say, a thing that's 5 to the k plus 13 to the j, say, then if k and j are smaller than the maximum, then this term is at most essentially 1/5 the maximum. If the exponent of 5 is 1 less, then the whole term is basically 1/5 the size of the biggest term. And that means if the terms are sort of n plus d, n plus 2d, etc., then that term has to be basically n, because 5 times n plus d is going to be bigger than n plus 5d, for example. And so really the elementary arguments become very, very simple for a and b large. So the a and b large we can just take care of with elementary arguments, even assuming there's only five terms in arithmetic progression. The difficult bit becomes, there's some combinatorial arguments involved. The difficult bit becomes when a and b are quite small. And that's why, if I step back here, we can get away with the case where we need five terms, where a and b are just 2 and 3. For this one, for the 4-term and 3-term, a and b are still relatively small. So these are not valid for arbitrarily large a and b, but they're good enough for our purposes. So this is a case where, again, we essentially take care of, for our overall theorem, we're taking care of a and b large by purely elementary arguments. And then if b is the largest thing, we basically bound b by 13, and then we can apply all these arguments to take care of the special cases with small a and b. And that's where you have to work hard. And by far the hardest case is when a is 2 and b is 3. And again, they were able to get a bound of less than or equal to 6, but to actually classify the results where you have 5 and 6, that requires quite a bit of work. So the last thing I wanted to mention, a result that we use repeatedly in this, is a strange looking result. So the other results are all based upon bounds for linear forms and logarithms. This result is not. So this is a piece of machinery that is actually based upon Frey curves, as in Weyl's proof of Fermat's last theorem. So it's a strange looking result. It's not clear why one would want to have it, except that, strangely enough, when I go through the proof of this main result, we use this about 50 times. So it turns out to be kind of a crucial result. And it's a very odd looking result. So it's just that if b is an integer bigger than 2, we can ask, when is the difference of powers of b just when does it have no prime divisors bigger than 3? And a very strange looking result. So, and this is a complete classification of it. So you can show that it happens basically in this special parameterized family when when b minus 1 has no prime divisors bigger than 3. And then the other cases are very special. They're for b is 2, 3, 4, 5, 7, 9, and 17. So these particular cases. And this goes back to an old result of mine on finding the when the product of two consecutive integers is a perfect power up to powers of 2 and 3. So this connects to sort of classical kind of Frey curve results where you're looking at attacking these ternary Diophantine equations of the form ax to the L plus by to the L is cz squared. So it's an old result, uses a machinery of mine with Chris Skinner's going back to the beginning of time. So this paper, I think, is from something like 2008. So it uses this paper. It's mostly this paper. There's a little bit of work around the edges to prove this. But this result, curiously enough, is something that gets used again and again and again. So it's the one that we use when we don't have control. So here, this is the hammer that allows us to take care of arbitrarily large B and reduce it to the cases where B is small, and we can use the explicit bounds from linear forms and logs. So this again, as far as I know, this is beyond technology that doesn't use this sort of modularity of Frey curves kind of machinery. So that is fundamentally used in here, as far as I know. I don't think it's possible you could prove this with linear forms and logs, but you'd have to be quite enthusiastic, I think. It would be hard to do so. So that's kind of where I am. I apologize. I told Ilker I have to run a little bit early to get my daughter to a medical appointment, so I thought I'd wrap it up here if that's okay. So thank
No,
you very much.
you're welcome. Thank you very much for this interesting talk, and thank you having your time, sharing your time with us. So, are there any questions or remarks? You have some congratulations message. Thank you message on the chat.
Oh, thank you.
Any questions?
Do you want to say anything about how you use the modular method in here?
Well, it's really in this proposition I've got here that this is the only place. So to some degree, I'm just recycling result from before, but it's to prove this result, you look at you look at particular cases. So it's ax to the n plus by to the n is cz squared, where the a, b, and c are just comprised of powers of 2 and 3.
Mm-hmm.
So this is sort of a Frey curves, I think, originally written down by Henri Darmon and then
Okay.
used by Chris Skinner and myself in a paper. So you pull these out and essentially try to see what sort of information you can get out of this. And these are ternary equations that you can solve a good portion of the time, but not always, but enough to do this particular result. So that's the only place that the Frey curve sort of the modularity of these representations attached to these curves. That's the only place where that's being used, is in this proposition stated here. So the other stuff, it's mostly so that kind of, if you like, that does the heavy lifting to get us down to bound A and B absolutely. And then after that, it's linear forms and logs all the way.
Thank you.
Sure.
More questions? So, thank you, the speaker again,
Well,
and
thanks very much.
just
Everybody stay safe in this crazy world.
yes, hopefully, let's hope for peace
Yeah.
for everywhere in the world. Just a short announcement. Next month, we will host Professor Hussein Mawasati from IMPA, Brazil, on April 7th. We will make the necessary announcements. Thank you very much, Mike. It was very nice to see you again after some time.
Yeah, thanks. It's been
And
far too long, so
yeah, indeed.
all
So
right.
thank you very much for everyone for participation, and see you in the next seminar.
All right. Take care, everybody.
Take care. Bye bye.
Bye bye.